Welcome back. All right, I would like to talk about neural networks. And the reason I want to talk about neural networks is in the next video, we are going to cover non-parametric models. And we are going to use neural networks, a very, very popular method in machine learning and control theory. For those who doesn't know, this is kind of introduction to neural networks. Basically, a neural network consists of neurons and their connections. Here is a picture. You provide some inputs to the neural network. In this case, we have S number of neurons, 1, 2, and S, and neural network will produce you an output. And here neurons are nothing but they include a nonlinear activation function. I'm going to talk about that. So here, this example is basically a neural network example, more precisely an artificial feed-forward neural network having one hidden layer. This is one hidden layer. You can have more hidden layers, and if you have more hidden layers, basically like you can provide more inputs to here. In this case, it will look something like this. And then, so in this case, if you have more hidden layers, then these network will call deep neural networks. So deep neural networks are just neural networks that have more hidden layers, and they tend to have a better, more close, a better approximation property. But one hidden layer neural networks are also great tools for the purpose of least squares. And I am going to demonstrate this with an example. All right, more specifically, I am going to choose this so-called nonlinear activation function to be basically, I am going to use RBF, radial basis functions, as our nonlinear activation functions because of their universal function approximation property that I am going to cover in the next slide. And radial basis function is nothing but exponential of some constant d1 that you need to choose, d2 that you need to choose, x minus d2 to the power of 2. Basically, d2, let me talk about d2. d2 is shows the value of this radial basis function center. It will be located at d2. And d1 is related with the width. So for example, if you increase d1, then you are going to get a narrower width. If you decrease it, you are going to get a width like this. And I am going to show an example at the end of this lecture so that everything will be crystal clear. Bear with me. Before that, let's talk about universal approximation theorem for radial basis function feed-forward neural networks. And I will be a little bit mathematical. Let y be a continuous function. Then this Euclidean norm will be upper bounded by epsilon over a compact set D. Compact set D is basically the set that we are approximating that function. Let's say, for example, this D is between -2 and 6 in the next example that I am going to show you. Theta of x here contains the basis function. Basically, it will contain radial basis functions and its entries. W will be unknown weights that we are going to find analytical solution. You can also find the gradient descent-based solution. Anyway, so basically what I am trying to tell is radial basis function single layer neural networks can approximate any continuous function up to any accuracy. So note that this epsilon approaches to 0 as S, the number of the radial basis functions that you are going to include here increases. Again, a MATLAB example will demonstrate that. So before we proceed further, let's say we would like to approximate this black function okay? And to approximate it, basically, I am using 4 radial basis functions. I am choosing the first one, red one, like this, and so that it gets, it is absolutely getting close to this black function, but it also has some contributions from the green, magenta, and blue radial basis function. And if you basically go and calculate, if you sum, let's call it y1, y2, y3, and y4, you are going to get exactly this black line. As you see, we approximate this black function using 4 radial basis functions. But I did this by hand, which can be really painful, and I don't suggest that. We are in the next video, when we discuss non-parametric models, I will automate this process. When we find analytical solution, again, you can use the gradient descent solution. You just write one line of a code and it will find automatically. Hand calculations are not included. Otherwise, finding this by hand, this fit, it will be really painful, right? You choose your first basis function to fit that. Then once you add the second function, you need to tune the first function and the second function a little bit. Then you add the third one, and this is really a lot of ad hoc process to perfectly match this black function, this function y. So we are going to do it using least squares and linear regression in the next video. The purpose of this video is, if you want to remember something from this video, remember that neural networks, especially radial basis function, one layer neural networks, are universal approximators. As you increase the number of these radial basis functions, epsilon converges to 0, and you will get the exact function. Again, sorry if previously in the video, if I mentioned you are going to see an example at the end. This lecture doesn't contain an example. What I meant is, when we cover the non-parametric models in the next video, an example using radial basis functions will be included. The purpose of this video, again, just to introduce you to the neural networks and their universal function approximation property. All right, so after these motivations, basically, thanks to the universal approximation theorem, we are going to choose in the next video, the non-parametric model like this. Y had to be the theta multiplied by W. I will treat W to be unknown, since I don't want to do this fitting by hand. I want least squares to find the solution, the best optimal solution for me. And theta will contain the radial basis functions. And this is the great tool when the relationship between a dependent variable y and independent variable x does not have a specific form. And basically, we can also approximate continuous functions using other techniques, such as polynomials or Fourier or Taylor series. So you may ask, where neural networks, radial basis neural networks, are not the only universal approximation. There are also other universal approximators like polynomials, Fourier, Taylor series. Why don't we use them? And I will give you precisely 2 reasons. First of all, radial basis function neural networks can represent complex nonlinear relationships in data, which might be difficult for polynomials or Fourier or Taylor series, without increasing their order significantly. Meaning that if you have really a complex function, and if you are using, for example, polynomials, you need to increase the order of the polynomial and order of the unknowns W1, W2, W5, W100 significantly. And you can do this you can use much less unknown terms and much less, basically the order becomes much less with neural networks. That's why neural networks became extremely popular in machine learning and control theory. The second one, as compared to radial basis function neural networks, polynomials might overfit to data. I will talk about that. And Fourier Taylor series can suffer from the ringing artifacts. Okay, two maybe new words for you: overfit and ringing. Basically, if you have simply these 5 datas, and if you choose, when you use polynomial, if you choose the polynomial order to be high, then you may have, instead of having a nice fit like this, these large deviations, unnecessary deviations, are called overfit, right? You can have interesting cases, and polynomials are known to suffer from overfit. And Fourier or Taylor series can suffer from the ringing effect. I will use these data points, and I would like to fit a continuous function to these data. And you may have these interesting oscillations in your fit. These ringing artifacts, these are the ringing artifacts. Instead of having a nice fit like this, these are called the ringing artifacts. So to sum them up, radial basis function neural networks, or in neural networks in general, and their deep neural network versions, are just great to smoothly fit to data, and we are going to use it for non-parametric models in regression and control. Thanks.